morning, good afternoon, wherever you may be in your day. Thank you as always for choosing to make chemistry part of your day. We are done with the test 1 material. We are done with the test 2 material. We are moving on to test number 3 because there is no rest for the wicked or the good guys, the chemists. And with that being said, due apologies to everything in this chapter, the way I describe it to my physics engineering friends. Out there in the world, you know who you are. And this is Chem 101. It's Chem 101 thermochemistry. It's not an engineering thermochem. So with that being said, let's learn some vocab. I probably should have started with what is thermochemistry. It's the study of energy changes associated with chemical reactions. So thermo, energy, chemical, chemical. So we're going to look at reactions. Reactions go to paradox. Do they release energy? Do they gain energy? That's what we're looking at here. So it's basic thermochemistry. Reminder of the first law of thermodynamics, meaning you cannot win. We cannot create or destroy matter or energy. So again, we can transform it, and that's what I want to talk about on this slide. But before I do that, let's talk about kinetic energy and potential energy. Kinetic energy is the energy of movement. This could be everything from light waves to the ocean waves to sound waves to heat. Physical movement. Movement of your electrons. Movement within a bond. Movement of bending, whatever you have. So just movement in general. And then we have potential energy, which I like to think of as stored energy. So you actually have the energy in a bond. If you were to break a bond, you know, that's what happens there. So we have stored energy. We have gravitational energy is a good form of stored energy. So this has stored energy. If I release it, it turns into kinetic energy, and then at the end it turns into heat and sound. You might have heard it hit. Or, if you wanted a more illustrative example, we could take something like the history of art. We could give it potential energy. It's further away from the dragon in the center of the earth that accelerates things at itself at 9.82 meters per second squared. We could release it, and you could definitely hear that. If you've ever stripped a screw, how does the head of the screw feel? Extremely hot. You're turning a lot of your stored energy in your ATP into heat energy on that screw as it doesn't come out as you strip it. So those kind of ideas. Energy transformation. We can transform energy, but we don't create it. We don't destroy it. We just change it from one thing to another. And really all of our energy is solar energy. Okay, so very quickly, when I flip a switch and the light comes on, what's going on? We're taking stored chemical potential electrical energy. We're allowing it to flow through the coil of the light bulb. It gets hot. It gives off light. Those are all energy transformations. So again, all these things that move. And I mean, if you want to go all the way back to where the energy come from, maybe it came from a dam, such as the Little River Dam, making Claytor Lake. There are sharks in Claytor Lake. You gotta be very careful when you swim. There's also these crazy goldfish. If you don't believe me about sharks being in random places, talk to Dr. Herman in physics. He sees sharks with her. You wouldn't think there'd be sharks. So anyway, so you got the dam. If you were ever at a dam, you'd notice it's very loud. You have sound energy, mechanical energy turning the turbine. You have gravitational potential energy turning into kinetic energy. There's a lot of things that play when we do even simple things, like picking up a book. I mean, you have literally my stored energy to kinetic energy in my muscles, to gravitational energy in the book, to kinetic energy, to sound energy, to heat energy. All of these things are occurring. So there's a lot of pieces going on. So again, you know, not to make it too simple here. Let's talk about chemistry. Chemical A, atom B. They could be, in theory, their nuclei could be touching, or their nuclei could be on opposite ends of the universe. And that's what the x-axis represents. This is touching, this is the other side of the universe. So at some point, you might imagine, if we pull these atoms apart, at some point they stop interacting. So that's this flat part. And this goes on forever. There's no interaction, the atoms are just the atoms. But then we have this point where they interact, and not only do they interact, but you get electrons between the two nuclei, they cement them together, we form a chemical bond. So this is a good state. This is a better state. So this drops down in energy, and there's an ideal distance. If they get too close, the nuclei start to repel each other, and you know that. And there's almost like an infinite energy up here at the top, because the nuclei would never touch unless you're really fusing them together. So then we're talking stars, nuclear bombs, things like that. So we're really talking about weird things at that point. So really, you don't see this part of the graph, but you got this little well. And what I want to point out is, that the atoms aren't always exactly the same distance apart. They vibrate. And there's a little bit of, the atoms are moving, they get a little further apart, and it's better to be closer together. They get too close, and they do this kind of vibrational. And that's what's happening at the bottom of this well. The flat part of the well tells you how much the bond can kind of breathe, if you will, or vibrate. It's a lot like a spring, if you look at the physics associated with this. So anyway, this is really a little bit better look at what we're looking at for chemistry. Hopefully that sets the stage for where some of this energy is, how we can release it, how we can store it. And let's talk about something very quickly, because every single general chemistry course in the universe talks about this idea of a state function, which means the path doesn't matter. What's it really tell us? It tells us that we can look at the beginning and the end, the products and the reactants, and we can ignore the middle. We've been doing that all along anyways, whether you realize it or not. But basically, the state function allows us to do math. And it's basically saying if chemical A turns into chemical B, and chemical B turns into chemical C, if we take the energy from step 1 and the energy from step 2, it equals the overall energy. So again, some of this is intuitive. If I burn 2 pieces of wood, it is twice as much energy as 1 piece of wood. You can add the first one and the second one together, and voila, that's your energy change. So kind of intuitive, but that's what a state function means. They use some silly examples like your bank account. Doesn't matter how many deposits and withdrawals you have. It's what do you have at the beginning of the month, end of the month. That's your net change in your bank account. Filling a balloon, again, doesn't matter how many breaths I use, but at the end, what's the size of the balloon? Elevation change is your classic. If I go from here to Denver, it doesn't matter if I fly, walk, drive, go through Texas, go through Canada, same elevation change. But the distance does make a difference, so the distance traveled changes. So that would not be a state function. We could not do this kind of math associated with it. This we're going to use a lot, this idea of system and surroundings. The most base, and a warning, if you ever take an engineering course, they do the opposite. Good news is no engineering at Radford, so hopefully this won't be confusing. Okay, so the simple definition of the system is what we care about. What are we studying? And we're in chemistry class, so we are studying the chemicals. So that's what we care about. We care about the chemicals. This is very sad because it means we don't care about ourselves. And typically, I don't know about you, I live in a Virgo-centric universe, so this chapter makes me very sad. I'm part of the surroundings, the everything else in the universe. I'm just part of the stuff. It's very sad. But we do tend to conceptualize things through our own experiences. And it is important to remember that what we're feeling is the opposite of what the chemicals are doing. So if we feel hot, the chemicals are losing energy. If we feel cold, the chemicals are stealing that energy from us. So just remember that it's kind of flipped. We're on the outside looking in. So surroundings is technically the rest of the universe, although for practical standpoints, it's the immediate surroundings. With all due respect to the butterfly theory, if a butterfly flaps its wings in China, it does not affect my classroom, at least at a measurable or significant amount. All right. So again, system, surroundings. Here's me. You can tell it's me because I got this periodic table with me no matter where I go. And I got a smile and some spiky hair and a goatee. So, definitely me. Okay. So, 2 more definitions. If the system is gaining energy and it has to come from the surroundings to the system, energy is entering what we care about. So we call that endothermic. Enter endothermic. If the system is giving off heat, radiating heat, like a fire, most things actually do this. Most reactions that you see do this. They give off energy. It's exiting the system. Again, the system is what we care about. Everything's in terms of the system, whether it's stated implicitly or not in the book. So if the system is losing energy or it's exiting, we call that exothermic. Remember, we're in the surroundings. So if it's leaving the system, we're gaining it. It feels hot. A thermometer reading in a word problem, getting a little bit more pragmatic, the number would go up. If energy is going into the system, it's going to feel cold, and pragmatically, if we're reading a word problem, the temperature is going to go down. There's probably a little bit too much on this slide, but bear with me here. If we want to look at the energy change of a chemical reaction, we could say it's made of 2 different components. And again, apologies to physics, skipping a lot of stuff here, making a lot of assumptions here. It's the sum of the heat change and the work done or done to the system. So, again, heat, Q, and here's a real chemical reaction. Propane gas can be burned with oxygen to produce carbon dioxide and water. So what would this look like? So heat's pretty easy in this particular case. This is a combustion reaction. We're adding oxygens. Remember, that means fire. Fire feels hot. Feels hot is on the losing side. Exothermic, that's going to be a negative sign as far as the value goes. Now what about this work function? And again, I'm going to skip all the physics. And we want to look at the number of moles of gas. So in this particular reaction, we have 1 of these and 5 of these for a total of 6 gas on the left. We have 3 of these and 4 of these, and they have to be gases. Have to be gases. Solids, liquids, just cross them out. Aqueous, cross them out. Ignore it. Just look at the gases. So we got 6 gases on this side, 7 gases on this side. That's going to expand. It's going to take up more space. There's more gases. To do that, you got to push back the atmosphere. So if we're pushing back the atmosphere, that takes energy. We lose energy to do that. That's not free. We have to move the air. And moving the air, that takes energy, so this would be negative and negative. And our total energy change here would be negative when we'd say this is an exogenic event, exothermic event, however you want to look at it, but it's losing energy. So let me summarize this, because I know I did that fast and I know it a little bit hectically. And once I drew it, I realized I had the info, but maybe I should introduce it a little bit cleaner. So Q is heat change. So we're talking temperature, thermometer here. Does it go up? Does it go down? If it feels hot, temperature goes up. It's exiting the system because we can't measure the chemicals. You can't stick a thermometer inside an O2 molecule. We can see how the O2 molecule affects the environment around it. And the thermometer is always part of the surroundings. So if it feels hot, temperature goes up. Exothermic, it's a negative sign as far as the value goes. We're not going to do the math yet, just qualitative. Endothermic, energy is coming in. It feels hot. It's gaining energy. So that's going to be a positive value for the heat change, or the heat associated with that. The energy is the sum of the heat and the work. And again, we're just looking qualitative. I want to be able to say, is it positive, is it negative, is it zero? So this is either temperature will be given to you, or we got to use a little bit of common sense. If it's a combustion reaction, if it's fire, we know it gets hot. Otherwise, it'll be given to you. And then as far as the work function goes, again, if temperature goes up, negative, temperature goes down, positive. The work function, we have to look at the change in gas. It has to be gas. So delta always means final minus initial, or change. Delta means change. 3 lines is defined as opposed to equal sign. And this is going to be equal to the final minus the initial. So in this particular case, this would be what? It would be moles, N means moles. Moles of product minus the moles of reactant. And that's moles. Just so you got that. All right, so you just want to take the final minus initial. So in that previous problem, we could do 7 minus 6, which equals positive 1. So if it's positive, that means we're expanding and our work function is negative because we have to push back the atmosphere. If we lose gases, if it's a negative value, that means it's going to contract. The atmosphere does work on us, so we get to gain that energy. As the atmosphere floods into us, we gain that energy. And remember, we're a chemical. We're not a human. Although I suppose humans are made of chemicals. And then you might ask, well, what if there's equal amounts? What if they were all solids reacting or all liquids? There's no gases. Then we would say there's no work function, and the value of the work function is 0, or approximates 0. And that's that. Hopefully this made sense. We're going to start using this mathematically. We're going to start using this in word problems. And we'll use this vocabulary in this building set. But hopefully this made sense. Introduce you to thermochemistry. And as always, have an awesome, wonderful day.